Let's sketch a graph with these characteristics. So you may want to draw some axes and label it from about -4 to +4. Actually, you're only going to need -4 to +2, but whatever. So not going to label the y-axis. It's somewhat irrelevant. Not really something that we're going to worry about too much. We're just sketching a graph based on these characteristics. The exercise in this is really interpreting what all of these mean. So we're going to go down this list, and before we ever draw anything over here, we're going to just interpret what all of these mathematical symbols mean and try to figure it out. So let's start at the very top. So f of -4 equals f of -2. Stop right there. Whatever f of 4 is, it's also equal to f of 2. Okay, so if I plug in a -4, I'm going to get the same thing I got if I plugged in a 2, and I get a 0. That means I have x-intercepts at x equals -4 and at 2. Alright? If you wanted to come over here to the graph and put a dot here and a dot here, you could. I'm not going to hold off. Alright? F prime of x, the slope of my original function, is represented by f prime. The derivative of x is less than 0. My derivative is negative for all my x values that are less than -1. Alright? Let's think about what that means. My first derivative tells me where things are increasing or decreasing on my original function. My first derivative is negative. Okay? Well, if my first derivative is negative, then it is decreasing for all the x values that are less than -1. So, decreasing for x less than -1. Well, f prime is greater than 0, so this is increasing for x greater than -1. And f prime of -1 equals 0. Ooh, okay. So if my slope is 0, tangent line is like this, and that implies that I'm at a maximum or a minimum, or in some cases, if you have this little funky thing going on right here, if you have that, it'd be right there. That's where your horizontal tangent line would be. If it's a cubic function or a fifth or something like that. Nevertheless, I know that I have a maximum or a minimum here. I know it's not one of those deals that goes like that, like I just said, because here's why. It's decreasing less than -1. So from here over it's decreasing. From here over it's increasing. And if it's going down and then it's coming up, then right here is where it levels off, and this must be a minimum or maximum. Decreasing, then increasing. Decreasing, then increasing, must be a minimum. I have a minimum at x equals -1. Okay? F double prime of x is greater than 0. Alright? Second derivative tells me about concavity. Tells me about this, tells me about this. And it never gave any other extra stuff and said for x less than this or x greater than that. So this must apply everywhere. So this entire function is concave, greater than 0, up. So concave up, everywhere. Let's draw it. Let's start with our x-intercepts at -4 and +2. 1. There's 1. Okay? It is decreasing for every x value that is less than -1. Now, if you're tempted to go, psh, who said it was a straight line? And if you did this and you went, psh, well, who said that was a straight line? Actually, that would mean that at that point, at x equals -1, right there, sorry for the line that got crooked, but at x equals -1, you can have a derivative that doesn't exist, but instead I have a derivative that does exist and it's 0, so it's going to go down. It's going to be like a parabola. It actually is a parabola, parabolic shaped. So it's going to go down like this, level off there, and then come back up. And everything I just did is consistent with it being concave up everywhere. So here goes, final answer. Down, up. Notice it's concave up. Notice if I drew a horizontal tangent right here, it would fit perfectly. There we go. We have done that one. Okay, we're going to graph another one. Let me grab my eraser. Looking for it. It was right in front of my face. And, ooh, these markers erase well, except for the green one. The black one erases well. Orange and red too, just not the green one. Okay, so let's draw another graph. You already have these things on your paper, but I'm going to write them in green just so they'll be with me forever. So here goes. They said that f of negative 4, I'll write this quickly since you already have it, equals f of 2, which equals 0. You know what that means, right? X-intercepts. F prime of x is greater than 0 for every x value less than negative 1. F prime of x is less than 0 for x greater than negative 1. F prime of negative 1 does not exist. Let's stop and talk about that. F prime of negative 1 does not exist. There are a couple things that could potentially happen there, but we know this. It's not going to be a smooth thing where it exists like that last one did, like a parabola or something very smooth, like a sine curve, cosine curve. F double prime of x is greater than 0 with a little caveat where x is not equal to negative 1. Okay, let's talk about what all that means, and then we'll graph this thing. And we'll kind of talk about it and graph at the same time. X-intercepts at negative 4 and positive 2. I'm not going to label that. I'm not going to write it down and tell exactly what that means because you know that, right? All right, there's that. Okay, let's keep interpreting this. F prime of x is greater than 0, increasing, for every value that is less than negative 1. So there's this little like understood line here of there's going to be kind of a transition that happens at negative 1. Normally when we put a dotted line like that, you're thinking there's an asymptote. I'm just saying that there's something happening here and something different happening here, all right? And the something happening here is that this is increasing, so it better be going up, and it better go through that point. Increasing for every x value less than negative 1. This one is going to be decreasing for every x value greater than negative 1. And this point does not exist, and that has a couple, like I said, it has a couple implications. It could be a sharp point, or it could be a discontinuity. I'm having a hard time spelling a 5-letter word. Not discontinuity, I was going to spell disco, okay? Probably would be alright spelling discontinuity, but when it comes to disco, I just couldn't do it. I'm not a big fan of that music. Bad joke. This means it is concave up everywhere except x equals negative 1. See, f double prime of x greater than 0, but not where x equals negative 1. Okay, so let's think about what this means. And I'm going to put the markers up for just a second. And we're going to grab a flimsy ruler. Okay, this thing is increasing at x is less than negative 1. So there we go. Right? Cool? Good. But it has to be concave up. So I'm going to need to make this graph look kind of like that. I need it to tilt. Does it do this? No, it doesn't. Because then, on this interval right here, from here to here, it would be decreasing. I don't want it to be decreasing. I want it to be increasing all the way up. This is concave up right here. Completely concave up. It's okay to have an asymptote with concavity. It's quite alright. So, concave up. This is decreasing, but still concave up. So it's doing this. So what this means is I have a sharp point, or I have a discontinuity, which could be a vertical asymptote. I'm going to go ahead and start drawing it. So there's this thing happening here where it's going like this. And here's one that's going down like this. Am I implying a vertical asymptote? Sure. They're not specific enough to where I could say what really happens here. I'm going to make it a sharp point. If you draw yours as a vertical asymptote, you're still safe. You're still good. They never said the value of the original function at negative 1, nor did they say the existence of the original function at negative 1. They just said that it's concave up everywhere except there. So at that point, we can't really talk about the concavity. So there's your graph.